Thank you. It's anything B or S equals just
All right. What page were we on? 149, 150? Cool, let's take a look at page 149. What questions did you come across on 149 last night? Yeah, Christian.
Let's go with 8.
8, you got it. Okay, so they both have negative exponents, which means they want to move. Remember, if they're going to move, it's either going to move from the numerator, the top, to the denominator, the bottom, or from the bottom to the top. So this wants to move down, this wants to move up. So that's going down, that's going up. So I'm going to get y squared over x to the third. And once you move it, you no longer have a negative exponent. Or, yeah, negative exponent.
It doesn't matter if they're not together, like they're not the same.
Just okay. What else would you like to see? 140, 149 front page. What about 150? Or anywhere on the worksheet?
18.
18? You got it. All right, so there's kind of a lot of rules on this one, and we can do a plethora of them. So I'm just gonna highlight this one. I'll highlight this. That's the only one that's gonna switch spots. Does that make sense to say that? But let's do all of the multiplication and combining of like terms. So I'm gonna multiply 3 and 2 together to get 6 on top. 4 times 3 gives me 12 on bottom. Now we might have to reduce at the end, but does everyone feel comfortable so far with what we got? And then the x squared and the x to the fourth, being we're multiplying, we're going to add the exponents there. This wants to move up. And then that stays down there. Now the problem's not done, but do you feel comfortable with the arithmetic that we did? Part of that you're questioning. Okay, so it looks like I could reduce 6 and 12. 6 over 12 reduces to 1 over 2. Is that okay? X is all by itself. There's not something on bottom, but then I can do a tug of war with the y's. Who wins, top or bottom? Top. Top by how many? 2. And then I don't really need that 1 there. I could keep it there. That'd be fine. But the more preferred answer would be this. That A-okay? Yeah, 20.
Oh, man, 23.
All right, remind me of 23 because I'm going to forget. 20. Let's hit 20 first. 20, we got negative 30, x to the negative 4, y to the negative 7, z to the 8. Over 15 x y to the negative 9 and z to the 10. Okay, so I'm going to highlight the things that want to move first. I'm not going to do anything else. Okay? Now where people start getting confused on this is they start thinking, oh, it's a negative number, so that needs to move. No, that negative 30 stays there. Okay, but this wants to move. This wants to move. And this wants to move. That negative 30 is just a negative number. It's not a negative exponent, so it stays in place. Yeah.
What is different about them that makes them want to move?
The exponent itself is negative. When the exponent's negative, it wants to go from top to bottom or bottom to top. Wants to change. It's needing to change locations. Okay, so let's rewrite this whole problem without doing any reducing, just with the things that moved. So Z the 8's still up there, Y to the 9's up there. We'll change the order of them eventually. So that moved up, and then X to X, and then Z to the 10, and then X to the 4th, and Y to the 7th. Now they're out of order right now, but that's okay. We'll settle it up. Do you feel comfortable with everything that moved? Are there any more negative exponents up there as it sits? Again, the negative 30 is a negative number, so it's going to stay as a negative number. All right, so let's go through. I can go ahead and reduce those. That gives me negative 2 on top. Is that okay so far? All right, so let's take a look at the Z's. I have Z to the 8 on top, Z to the 10th on bottom. Tug of war, who wins, top or bottom?
Bottom.
By how many?
2.
2, so Z squared on bottom. Okay, let's take a look at the Y's. Y to the 9th here and Y to the 7th here. Tug of war with the Y's. Who wins, top or bottom?
Top.
By how many?
2.
2. Okay, and then so we took care of the Z's, took care of the Y's. Ooh, let's take a look at the X's. What do I do with the X's? Is this X to the 1st?
Yeah.
So what do I do with those now? You just combine them so that I get X to the 5th, right? There's my answer. So I think these are really doable problems if you slow it down and you write your steps out. The problem is a lot of students, they want to sit there and say, oh, I can cram 6 steps into one. It's like, I'll leave space. Don't worry. You got plenty of paper. Uh-oh. Oh. It's not just you. It should have been a ta-da.
Ta-da.
Yes. All right. What was the other one you wanted to?
23.
23. Yeah. 23. All right, I'm just going to highlight the negative exponents first. I'm not going to do any other arithmetic. So let's just highlight. Let's highlight what's going to move. So that is going to move. This is going to move. This is going to move. And this is going to move. Is that okay? So did I highlight all the negative exponents? So, did you get it?
Yeah. Nice. You are God.
Yeah. Let me freeze this real quick. All right. S-A-R-R-E-T-T? A-T-T. There you go. You got it.
Yeah.
You got a 6 out there.
Yeah.
I hate you.
Sweet.
You made it. If you're a sophomore, you would not have to worry about it. Graduate. Be satisfied. You want to do anything else today? You want to do anything else?
No, I have to pick up another
That's not what I'm saying.
grade, so that's the thing I can do that either tomorrow or Friday. Perfect. That'll be okay.
Works. Yeah. Totally. Good job.
Thank you.
And you know the 6 out of 10 gets you the 20 out of 20 quiz score. So.
Thank you.
Yeah, buddy. All right. We're unfrozen. We're good. All right. So let's rewrite this with no negative exponents. got it. See you tomorrow.
See you later.
Look forward to it.
That's not.
All right. Did I make all the appropriate movements? Does this all make sense still?
Yes.
All right. So we could, if we wanted to, we could maybe start reducing. We could say, hey, that goes into there 3 times. What do you think? And then that goes into that twice, right? So on top, it looks like I have a 3 over a 2. Let me just pause there a minute. Does everyone feel comfortable with the math? All right, so let's take care of combining the y's. So how many y's do I have on top now? 5.
That was it.
How many x's do I have on top?
8.
How many x's are on bottom?
4.
How many y's on bottom? 15. Okay. So the 3 over 2 stays as is for right now.
Thank you.
Blessing you.
Thank you.
All right, so let's take a look at the x's. Tug of war with the x's. Who wins, top or bottom?
Top.
By how many?
1.
How many x's do I have on bottom?
4.
How many on top?
Oh, I was.
So how many?
One was 4.
4. Cool. Tug of war with the y's. Who wins, top or bottom?
Bottom.
By how many?
10.
There you go. That's it.
If you stop wearing shorts, always wear shorts. Because.
Anything else?
What would happen if you multiply first?
Oh, then you just have to reduce. So if you were to multiply first, let's see, I could get 12 y to the third, y squared, x to the fifth, x to the third. Oh, wait. Why am I doing that? I'm being silly. Sorry. So that gives me y to the fifth on top, x to the eighth on top. And if I multiply 2 and 4, I'd get 8. Okay, and then I get x to the fourth, y to the 15th. And then you'd have to reduce that. So 4 goes into both. So 3 over 2. And then everything else is the same.
So it works as well.
There's not a more correct way to do it. So it's just based on preference. I guess if you were to talk about like really big numbers, it'd be nice if you could reduce it to smaller originally, but it'll get there. Anything else you want to take a look at? To where? 2, 4. A to the 0, b to the negative 3, over a to the fifth, b to the negative 2, a to the fourth, b to the negative 2, over a to the negative fifth, and b to the fourth. All right, I'm going to highlight. I'm going to highlight in one color the negative exponents. So this wants to move. This wants to move. This wants to move. And this wants to move. Then I'm going to highlight this one. Why am I highlighting that one?
Because it's a 0.
Yeah, it's a to the 0. What is a to the 0? 1. 1. That just gives me a 1 right there, right? All right, so let's rewrite this. So I know that this is a 1. And let's rewrite it with the things that we know. So b squared, a to the fifth, b to the third, times a to the fourth, a to the fifth, b to the fourth, b to the second. Does that seem okay so far? I probably won't need that 1 out there, but just wanted to show you where it took place. We good so far? All right. So let's take care of what's on top. So I get b squared, and then how many a's are on top?
9.
9. Cool. How many a's are on bottom?
9.
How many b's are on bottom?
7.
6. 4 plus 2, 6. All right. Tug of war? Tug of war with the A's. Who wins, top or bottom? Top by how many? 1. So A to the first is the same thing as A, right? Does that seem okay? Tug of war with the B's. Who wins, top or bottom? By how many? 4. Yeah, that's done. Ooh, that big old thing just reduced down to that little tiny thing. Cool. All right, if you would, make sure your name is on that as well as anything else you might be submitting. And turn it on in. Ready to go? 47. Your name. To you. This one. Thank you much. Thank you much. What's that? No.
Right. Instead of show, I'm bringing solidify, I'm bringing.
All right. One last property we're going to look at, and then we're going to look at scientific notation a little bit. But there's not really a lot of notes. So the one rule we're going to look at is what happens if I have x, y, say to the 5th. This is going to turn into x to the 5th, y to the 5th. It distributes to both. Yeah. So if I had like 2x to the 3rd to the 4th, that's going to give me 2 to the 4th. And I'm sure we'll be able to figure that out. And then x to the 12th. And 2 to the 4 is 2 times 2, which is 4, times another 2, which is 8, times another 2, which is 16. So I get this. So that's basically the rule we're going to look now. So if we have this exponent outside and you have like kind of more terms in there, that distributes to all of them. Okay? And then the last thing that we just want to take a look at is scientific notation. And again, so scientific notation came around a long time ago to deal with when you had really large numbers in order to be able to multiply them and divide them quickly. After scientific notation went out, or it kind of went out, but it's still very much used, then they discovered something called a logarithm. And a logarithm is the LOG key on your calculator. I don't know if you've ever seen that. And then there's actually the natural log, which is the base E of a log, which, don't worry, you don't need to know those at this point. But logarithm and natural log started dealing with just with the exponents, because the exponent's what makes a number grow rapidly, okay? Or it makes a number get to a really small decimal, like some decimal has a whole bunch of zeros. So scientific notation was designed when you have a huge number. So let's say we have I don't know. Okay? So scientific notation is going to be written this way. A single number, and then up to 3 decimal places times 10 to the some power. There's going to be something that we put there. Okay? So what I want to do is I want to take this and I want to make it 9, 3, 1, 2. I'm not going to worry about the rest because they're not as large of a number, but we're going to deal with this as scientific notation. So where does the decimal sit right now on my blue answer? If it's not, if we can't see it, where must it be sitting?
Between the 9 and 3.
Well, it will be at the 9 and 3 here, absolutely. But where will it exist up here? Does anyone see a decimal up on this one at all?
No.
Okay, so it's got to fall right here. Okay, that's where the decimal falls. Is that okay? So what we're going to do is I want to get the decimal from there to here. So we're going to count. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So again, you're not really worried about numbers beyond, 3 decimals away from it. Okay, you're talking about just major numbers. Okay, so that's kind of the first thing we want to take a look at. So, if I went backwards the other way, let's say I have 4.623 times 10 to the 12th power. Okay, and I want to convert that back into a decimal. So I know I have 4.623. So how many times will I have to move the decimal this way based on this? 12. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So I don't even know what that number would be. There. 4,600,000,000 no, that's even more. 4,623,000,000,000 is what 4.623 times 10 to the 12th power would be. So if you're making it in scientific notation, you have to realize where did this decimal fall, move it back, and on this one, if we want to convert it out of scientific notation to a big old number, we can. Okay, so scientific notation works really well with big numbers and it works really well with small numbers. Now let's take a look at a small number. So let's say we had that's tiny. It's like, hey, do we got enough pennies? That's pretty bad. Okay. All right. So let's talk about how we're going to make this in scientific notation. So I want that decimal to be right here. So now I have 4.623 times 10. Now let's move the decimal all the way there. So I'm going to move 1, 2, 3, 4, 5, 6, 7, 8, 9. And I'm going to put it to the -9 power. If I put it to the -9 power, that means I'm talking about an itty bitty tiny decimal. Okay? Itty bitty tiny decimal. But then, let's say I was given this type of problem where I had 8.317 times 10 to the -7 power. So it's to the -7 power, so it's going to move. So I'm going to put a decimal here, and I'm going to go, I need to move this decimal this way 7 spots. So I got 1, 2, 3, 4, 5, 6. So it was from here to here, 7. 1, 2, 3, 4, 5, 6, 7. Yep. Now, let's just talk about what this all kind of means. Like, let's put something into perspective that maybe we could put our eyes on something. I'm going to use a calculator because when I ask you guys to use a calculator, you sit there and stare at me. Okay. Has anyone in here in your science class heard of a term called Avogadro's number? You ever heard of it? You've heard of it? So in your science class, you might have seen Avogadro's number up on the wall, which is 6.02 times 10 to the 23rd power. Okay? So if I wanted to write that without having a decimal, I'm going to go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 17, 18, 19, 20, 21, 22, 23. How big's that number? Well, I don't know. That's there's your millions, billions, trillions, 100 trillion, billion trillion, trillion trillion, 602 trillion trillion. Yeah, I'm sure there's some route we can go to, but it becomes goofy to.
Why can't we just come up with standard suffixes
Because nothing's gonna get
trillion,
nothing's gonna get that big.
but like
Sure, he's not on.
distance
What?
in the galaxy, like not the galaxy, but the universe will eventually be. So like, why don't we just come up
If
with
the galaxies continue to expand, we'll never get to the end of it. And being that it's expanding at the speed of light, we will never truly get to the end of it.
Yeah, then
We'll never
like,
truly what?
shouldn't we be able to come up with an estimate of it at like the size
Well,
of a certain time?
So it's moving at the speed of light. So right now, the galaxy is one size, and right now it's much larger because that 2 seconds it took me, how far did the speed of light actually travel? So it's a number we can't fathom. But let's talk about something that we look at on the ground. You see a penny, sometimes you pick it up, sometimes you're like, it's just a penny. So let's say we had that many pennies.
How do we catch it?
That many pennies, okay? You with me on this?
What do we divide by 100?
All right, so let's do this. Y'all got a phone?
No.
Somebody ask Siri or whomever, how many people are on the planet right now?
Like 7. No. There's a 7.
Y'all got a phone, pull it out!
You don't have a phone? I don't. You don't have a phone?
I'm sorry.
We have an iPhone.
How many people are on Earth right now?
7.7 billion.
7.7 billion, thank you. So let's talk about, this is the number of people right now. So 7.7 billion is this,
Some people have more money than that.
okay? So that's 7.7 billion. You with me? So, if we were to say, okay, let's say we had 6.02 times 10 to the 23rd pennies. That is a lot of pennies. So I'm going to do this. I'm going to say, okay, well, that's fine. So 602, and then 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0. It almost goes almost all the way across my screen. Divided by 7, 7, 0, 0, 0, 0, 0, 0, 0, 0. Holy cow. That means there's 1, 2, 3, 4, 5, 818, 13. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. So that's how many pennies each and every person on the planet right now would get. And you're like, oh, so what? It's just pennies. Okay, well, let's divide that by 100. So that means each and every person on this planet would get this.
Well, then the worth of a dollar would go way, way, way down.
Thanks for adding to the conversation. 181.
It's true though.
Stop. Come on, man. You gotta look so deep and stuff. Like he's trying to do a math problem. Come on now. For sure.
So this would be how many dollars every person right now on the planet would have. 781,818,181,800. Anyone want to take a challenge on how much that would be that we could spend per day?
Probably.
So the average person lives 81 years. Okay. So that means that you could spend $9,652,076,319 a year. So let's see what that fathoms in today's, divided by 365 days. So that means that you could spend 26 $6,444,044.71 a day you would get to spend for the rest of your life.
Would that be how much money it would to take to like empty out your bank account of that, or like would you still have more?
You still have more if you didn't live as long. So that's how many days. Let's divide that by 24 because there's 24 hours a day. That's going to allow us to spend $1,101,835.20 every hour you get to spend. Let's divide that by 60. That means that we get to spend $18,363.92 every minute. Divide that by another 60. So we can spend $306.07 every second. I'm up for the challenge. What about y'all?
Just like Bill Gates.
Bill Gates doesn't have that much money.
Yeah, but like nothing doesn't even have to think about money.
Holy cow.
Really, it's just for men.
Wow. Numbers can be pretty darn big, huh? But I think that kind of gives perspective what that would mean. And Oliver's right. If everyone had that much money, the value of the dollar would stink. But just trying to say, well, what if we said we had Oreos, did the same thing? So we would be able to eat 306 Oreos every second for the rest of our lives.
That's what kind of Oreos you did.
We'd big and would be as round as this room. All with diabetes. And they'd have to be cut body parts off because we would get bad circulation in our extremities. Yeah.
So like, I think this is a little bit off. This is totally off topic. Okay. So like, how long would it take, like, if we didn't eat that much? How long would it take to like for our bodies to process like all that? I just like
300 Oreos.
Well,
300 or
a second.
Well, wouldn't you throw up?
oh yeah, your stomach's gonna sit there and say what? Because so from the back of your throat all the way through the back end where poop comes out is something called pyloric waves, and they take place, and that's how your esophagus pushes your food down your stomach. The stomach kind of massages back and forth using something called pyloric waves to move the food that's in there back and forth in hydrochloric acid. That's what's in your stomach. And then as your stomach breaks it down to a smaller level, because the acid always is doing it, your stomach isn't absorbing any type of nutrients. Some people think, oh yeah, your stomach's really important. Yeah, it is, because it does this. It washes whatever you just ate in hydrochloric acid to break it down to a smaller form, so then you can go into your small intestines, which is not a tube. Your small intestines actually looks like, the best example would be pineapple rings. I don't know if you've ever taken it. That's what it kind of looks like. So it's spread out, so you create a large surface area, and by you creating a large surface area, that food then goes through there and is absorbed, and it's about 16 feet long, 16 to 23 feet long, depending upon. Yeah, so that is absorbing any of the nutrients from the food you ate, and then it goes to your colon, which is, you have your ascending, transverse, and descending. The descending goes out the back door. That is anywhere from 3 to 6 feet long, depending upon the person. And that's called your colon. It's called your large intestine, which is your colon. All your colon does is it absorbs the water from what you have eaten, and it allows it to go into a solid form so you don't become dehydrated. And then you expel whatever your body couldn't absorb. And there is your, now the cool thing about pyloric waves is they can work backwards too. That's when you're like, you eat something bad, no, I don't feel good, you go blah. So the pyloric wave says, hey, and it actually expels things faster than it goes the other way. So pyloric waves going backwards allow you, so if you were to ever throw up, boom, it gets rid of it quickly.
Isn't it called like projectile vomiting?
Projectile vomiting.
Ew.
It's just plain funny. You watch people barf, that's just entertainment.
Wait, how come if we smell barf, we tend to barf?
Because you're smelling the bile, you're smelling the unprocessed food. So the food that's in your stomach had gone through the process and it is starting to break down. And so when you throw up, you have the bile and the breaking down of rotting food, basically, is what you're smelling. So it is an unpleasant scent. So if you're right there with it, it's going to give you a gag reflex. And it's a natural reflex. So, and there was actually a study done many years ago, and I'm sure this is different now, but I remember there was a study they had us read in one of our psychology classes I took, and they were talking about the worst smell known to man at the time was rat vomit after eating human waste.
What?
Human waste is like
Poop.
Poop. How on earth would you get hold of that stuff?
I don't know. It just sounded like a great thing going. And I mean, you just think about it. Okay, a rat that was eating poop, human poop, that barfed. That supposedly is the worst smell you could ever come across. Yeah.
How long will humans evolve more?
Huh?
Will humans evolve more?
Will humans evolve more?
Yeah.
Yeah. I mean, things that we evolve to. There's certain organs in our body that we don't necessarily use. They might, at some point, after 1,000 iterations of procreation, they might go away. But like, there's certain things in our body that we're like, that's a useless thing.
Go up to it.
Because we used to eat hair and bone.
And smell it.
it's right in front of
So like, think about
Oh,
like
they smell that?
in our lower end states, or even a couple hundred years
I
ago.
didn't know that.
You go out and you shoot a rabbit. You try and get as much hair off as you can, but you're ingesting some of that hair. Right now, if we ingested hair, it's actually the same effect as if you ingest large amounts of celery, because celery won't break down, and it's called a gastric beezer. It's called a hairball, and you get it in your stomach. And the only way for that gastric beezer to be expelled is you have to be like a cat and go, and it'll eventually come out. Most people will never get a gastric beezer, even though anything we eat, we will ingest a small portion of hair, because you never know what had fallen onto our food. It's kind of going gross, but some people with psychological disorders, they actually pull their hair out and eat it, and they
Oh my
develop.
gosh, I know a girl who does that.
Oh, remember that one girl?
It's a psychological disorder. I'm sorry, your friend is. Does that? How much of her hair does she eat?
Basically the top of her head is bald and then she has just like little strings.
I promise I didn't eat any of my hair. It just naturally falls out. All right, page 151, 152. Page 151, 152 is what I'd like you to do for tomorrow, please. Sound good?
She doesn't care.
We'll talk more silly stuff about.
That's my joke.